So about the atomic theory. So firstly, we here we introduce the law of conservation of mass. So this means after the reaction, the total mass of the matter will not change. Will not change. For example, we know hydrogen and the oxygen can react to form water, right? So before the reaction, the total mass of hydrogen and the oxygen is equal to the mass of the product. So this is about the law of conservation of mass. So now this is very simple, right? We know this law, but it's before 300 years ago. Okay, more than 200 years ago. So people have very few equipments. So also using this kind of experimental condition is not good, right? So this is the first law about the reaction or about the atom. Okay, now here's a question about this law. Potassium chloride decomposes to potassium chloride and oxygen when heated. In one experiment, 100 grams of potassium chloride, it will give 36.9 grams of oxygen and 57.3 grams of KCl. So what mass of KClO3 remained unreacted? So how to solve this problem? So we can just use the law of conservation of mass. So this means the mass before the reaction should be equal to the mass of the after the reaction. So here we know the mass of before the reaction, right? And after the reaction, we get these two mass. Okay, and what the mass remained after unreacted? So anyone want to have a try?
5.8.
5.8.
Oh, how do you get it? So just
you add 57.3 plus 36.9, then
yeah.
you subtract 100.
Yeah, good. Yeah.
So since we know potassium chloride, there are oxygen different masses, and we're supposed to break it down.
What?
I mean, since KCl equals B, right?
Yeah.
Each element there is potassium, the chlorine,
yes.
and the oxygen
yes.
all have different masses, and we're supposed to break it down.
No.
Looking at the way the periodic table is.
So in this case, we don't need more details about the potassium chloride. We just need it using this law. This law means the mass will not change. Okay. And of course, this is not. We will introduce more about what the reaction happened. Okay. But here we just need using this law to think out this question. So like the total mass before the reaction is 100 grams, okay? And so the total mass after the reaction should be also 100. So we're just using 100 minus these two mass, so we can get the mass unreacted. Okay? The second one is about the law of definite properties. Definite properties.
Proportions.
The definite proportions. This means in a given chemical compound, the proportions by mass of the elements that compose are fixed regardless of the source of the compound. For example, the water. So you can get the water like from the river, right? You can also get from some ice. But no matter where you get the water, its proportions should be the same. It's always H2O, no matter it comes from a river or ice. So this is about the law of definite proportions. So any questions? Because? Oh, okay. Okay. Oh, the answer is almost the answer. So here's another question. So, for example, in a set of experiments, very pure tin was combined with bromine, forming the bromide. So using this data, so confirm this law. So basically, this data are from experiments. Okay. So using this data, how to confirm this law. So basically, we just need to determine the ratio of tin and bromine, right? So we know the mass of tin. We know the mass of the product. So from here, for example, from these two mass, we can get the mass of bromine, right? Because the tin, the mass is this number. A tin and for bromine is this number. So this number minus this number should be the bromine, right? Should be bromine. So here, so the grams of tin is this number. Gram of bromine reaction should be this number. Okay. So the ratio of tin and the bromine will be using this number divided by this number. We can say it's almost the same, right? So what this means? So this means in different reaction, after different, we can use different mass to get the product. But in all this product, the ratio of the tin and the bromine should be the same. Should be the same. Okay? No matter the product come from which reaction. Okay? The final ratio should be same. So this is law of definite proportion. So it means the compose should be fixed. Okay, so this is from this example, we can confirm this law. Okay. Now the third part is about the Dalton's atomic theory. So Dalton raised this theory in 1766. So this is also the first theory about atom. Okay. So he said all matter consists of indivisible atoms. So at that time he think the atom is indivisible. Indivisible, okay. And the atoms of one kind of element are same in mass and properties. And the atoms of different kinds of elements are different. So like copper and gold, so they have different atoms. And one element is only made of by one kind of atom, And the compounds are made up of definite numbers of atoms of the complex elements like water. Okay? And also the weight of a compound equals the sum of weights of the elements. So in this theory, the atom is just like a ball. Okay, just like a ball. So this is called Dalton's atomic theory, and this ball is indivisible. It's just a whole ball. Okay, it's indivisible. So this is the first atomic theory in the history. Okay, now we know we can ask the question: are atoms really indivisible? Yes or no?
No.
No. Yes, of course. And after as time goes on, people found some new experiments, and from the new experiments, people found the atoms are not indivisible. For example, this is a very famous experiment. It's called cathode rays experiment. So basically, in this experiment, this is Thomson, and he did this experiment, and he found when the cathode rays is kind of like particles, and the particles, when it goes through the magnetic field, it will change its direction will change. It means the rays could be reflected by a magnetic field. For example, if we turn off the magnetic field, if you just go it will touch here, it will not change, right? Change the direction. If we turn off the magnetic field, and if we turn on, so it may go up. And if we change the here to NS, we change change these numbers, okay, and then it will go down. So this means the cathode rays should have charges, and they call it has lactivity. It is lactive. Okay, and also he raised the electron. This concept, the electron concept, and the electron is lactive particles, and so because it is lactive particles, so under the magnetic field it can change the direction. Okay, and also he also calculate the charge of each particles. And also the weight of the electrons and Millikan, he designed he designed an experiment, this experiment, to calculate the mass of the electron. So it's called oil job experiment. So in this experiment, this oil, they are negative. They have negative charges, and so this is so in this electron field, so we can change the volts of the field of the electron field, and at 1 volts, so the oil job will just stop here. We just stop here. So why it will stop here? Because there are two forces. One is we know it has gravity, right? And because it is selectively charged, it has electric charge. So it also has one force up. This is electric force. When these two forces are equal, so it will stop here. Okay. So we know this is relative to its mass, right? And this force is relative to the electron, to the electrons, to the elective electron. So we can calculate when these two forces equal, we can calculate the mass of the electron. And using this experiment, he found the mass of the electron was 9.1 times 10 to the power of minus 28. So it's very close. Now we know the actual mass of an electron is this level. Now we know, using more modern equipment, to find the mass of the electron is this level. We can see this number is very close, right? It's very close to the number, very close number. So, but this is about 100 years ago. Okay, 100 years ago, this experiment. So now we know for the atom, for atom, it includes some particles with negative charge. We know atom is neutral. So this means there must be some positive species in the atom, right? It can contains the electric charge. So this means the atom should include some negative particles and also some positive particles. So this means the one atom includes more particles. So, and then the Thomson, he raised the second atomic theory about the structure of atom. So it's called Plum-Pudding. You know pudding, right? You know what is pudding, right? And many people like pudding, right? So yeah, he said the atom is like a pudding. This means, for example, like this way. So the atom has the positive charge, okay, like a ball, okay, and it also includes some electron. The electrons are negative charge. So the electrons like stayed in the positive body, in the positive ball, Okay. So this is like a pudding, So it's also called like Plum-Pudding model. Okay. This model is better than Dalton's model, right? Because Dalton he just thought the atom is a ball, Okay, it's just one ball. Okay, and it's indivisible. Okay, but in this model, it's of course it's like a ball, but it includes different particles with different charges. Okay, so this is about Class1.2 model. Class1.2 model. And then people found some radioactives. Some atoms they have some radioactivity properties. This means they can emit some high energy radiation. Okay, and also the particles is not only like electrons or not only one. They are different radiation. They are different radiations. For example, Rusev and he found basically there are 3 types of radiation. So alpha, beta, and gamma radiation. And also alpha and beta radiation are banned by an electron field, but in opposite directions. Okay, so and the gamma radiation is unaffected. So this means alpha radiation is neutral. And so alpha particles have the charge of +2, and beta is -1. So besides electrons, there are also some other particles. Okay, and this is another very famous experiment in history. So in this experiment, so the alpha particle just hit the gold foil, and it found there are some particles were deflected through large angle, and could even be reflected back to the source, like this. Okay, it's like hit something and then reflect, and it is reflected. So the result of this experiment can't be explained using this model. So why? Because according to Class1.2 model, the density of the atom in everywhere are similar. Okay, are similar, right? Because it states the electron is a positive ball and also includes some negative electrons, and the density of the atom the density in everywhere is similar. Okay, so this means, but we also know the weight of the atom is very light. So this means the density of the atom should be very low. So it's very low when the particles hit the atom. It will just go through the atom, right? Because it's very light. The density is very light, so it will just go through. But in fact, there are some particles will be reflected by the atom. So these results can't be, the results of this experiment can't be explained using by this model. So, and then Thomson and Rusev, he raised a new model about the atom. So it's called nucleus model. So in this model, and we can say most of the mass of the atom and all its positively charged was locked in a centrifuge core. So this core is called nucleus. So this is one atom, okay? And it looks like ball, but most of the mass is and its positively charge is locked in the center of the atom. So here the density over here is very high, and outside here, the electrons are move. The electrons move here. Okay. So this means the electron is very light. So the density of this area is very, very small. Okay. But the density at the center is huge. It's huge. Okay. So using this model, we can explain the results of this experiment. So we can say here, in this model, when the particles when the particles hit the nucleus, so it will be reflected. If it doesn't hit the center, so it will just go through the atom. So using this model, we can explain the result of this experiment. So this is about the Rutherford's model. Is also called nuclear atom. So of course, this model is better than the Planck-Putin model, right? Okay. So and then people found more particles after the time of Rutherford, and then basically there are three particles we need to focus on. So one is electron, proton, and the neutron, So electron, we know it's -1. Okay, it's -1 charge, and the protons, they are +1 charge, and the neutrons are neutral. So basically, for one atom, it has equal number of electrons and the protons. The number of protons and the number of protons should be same, right? Should be same, and then the atom can be neutral. So one atom, atom has a unique number of electrons and the protons. And then so for this model, we can see all the protons and the neutrons are at the center of the atom, and the electrons move outside. And we can see the center is very small. If the atom was the size of a stadium, the nucleus would be the size of a ball. You know, this is not soccer, right? Not soccer. It's football, soccer. And football, yes. American football. Yeah. So this is huge, right? The stadium. If this is an atom, the nucleus is like a ball. So because this is very small, and also this means the density of the nucleus is very high. It's very high. Okay. And then after the Rutherford model, the 1913, Bohr, he raised a new model about atom, is called Bohr model. Bohr model. So in Bohr model, so and also this is one atom, okay, and it has a nuclear. It has a nucleus, okay, and outside is the electron. But the electron they move on certain orbital. They move on certain orbital, okay, and each orbital has different energy level. So this is also called orbital model. Orbital electron model.
So
Yeah.
they rotate around the nucleus. They do not cross.
No, they say like this. Okay, they just move like this. Okay. Of course, they will not hit each other. Okay, they just move on the other. The circle will not close, of course. Yeah. Okay. So this is the Bohr model. And in Bohr model, the structure we can also use it this way. Okay. So this is nuclear. This is nucleus. Okay. And this is different electron orbitals. Different electron orbitals, and also for example, some electrons move in this orbital, some in this, some are in this. They move in this, okay. And in this orbital, the electrons have the same energy level, okay. So in one electron orbital, they have same. And also, if the electrons close to the nucleus, they have low energy. If they move outside, so they will have high energy. So this is why the atom can emit light. Why they can emit light? For example, if one electron, let's say outside, right, they have high energy. They can jump to the low energy orbital. Okay, so the energy, so when they come to the orbital with low energy, so the energy will release like lit as light, So this is why they can emit, atom can emit light. And of course, if some electron move from inner orbital to outside orbitals, they should absorb light. Or absorb energy. Okay, the energy can be light or heat. Okay, heat energy or light energy. So this is about Bohr mode of atom. And now the most recent one is called the electron cloud model. It raised in 1926. And we will also introduce this model in the other chapters. Okay. So since atoms should be neutral, so the number of protons should be equal to the number of electrons. Okay. And atoms of different elements are distinguished by the difference in the number of protons and the number of electrons. So this means different atoms, they should have different number of protons or different number of electrons. Okay. So since the number of protons and electrons differ, so their mass differ. So these different atoms have different mass, And for example, hydrogen only one proton and one, of course, one proton means one electron, right? And the carbon have 6 protons and 6 electrons. So they have different number of protons and electrons, so they have different mass. And if atom have one electron or proton, we call it hydrogen. If it has 6, we call it carbon. Okay. So we also can using this way to describe the atom. So for example, carbon 12, 6, right? This is 1, 2 number here. So this number 12 is the sum of protons and neutrons. Neutrons, the atom also have neutrons. Neutrons is neutral, okay? But they have weight. They have mass, they have weight. So this number is the sum of protons and neutrons. And this number, 6, is the number of protons. So of course, the protons should be equal to the number of electrons, right? So if we know the number of protons, we also know its electrons. So this number, this number 12 is called mass number. And this number 6 is called atomic number. So each atom has its atomic number. And also we call this is mass number. In mass number, it doesn't include the weight of electrons. Why? Because compared with the protons and the neutrons, the weight of electrons is very, very small. We don't need to calculate its weight. Its weight. Okay, and we will introduce later. Okay, in this chapter. So here you should remember these 2 numbers. This is mass number. This is atomic number. Atomic number means which atom it is. Okay, mass number means the mass of the atom. Okay, here is an example. So for this, this is gold, okay, gold atom. So how many protons and neutrons and electrons are there in this guy? Yeah, it's answered, right? Yeah, we know this number is mass number. It includes protons and neutrons, okay? And this is atomic number is protons. So protons is also the electrons, right? So the electron. So what the proton? Of course, this is proton, okay? And this guy minus this guy is neutron, right? So here we can see 39 is the atomic number, and the proton is this guy. And the proton number should be equal to the electron number. So the electron should also this guy, okay? And this guy minus this guy, you will get the neutron number. Okay. Any question for this one? No. Good. Okay.